going to start our afternoon session of talks with Dr. Aisen Chacin. Um, she is the assistant professor of pathology at UTMB and director of the Medical Prototyping Lab, where she engineers a range of innovative devices that directly impact patient care. Her work integrates biomedical engineering with sensory augmentation, resuscitation technology, and surgical stimulation, advancing the field of medical device design. And the talk that they will be presenting is Medical Prototyping at the Bedside, Transforming the Process and Access of Medical Innovation.
Hello, everybody. How are you feeling post-prandial talk? So hopefully you're not passing out and you have more the less not hungry judge effect, which means you'll judge me favorably. If you don't know what that is, Google it. It's fun. So today I'm going to talk about medical prototyping at the bedside, transforming the process of access of medical ingenuity. I changed this last night because I thought innovation has this connotation of newness and more like patent oriented, right? Trying to, do the most innovative, the newest. But I thought ingenuity is better because it's about the quality of being clever, original, inventive, and not necessarily so stuck in being new. So I want to thank you so very much, OSHA. It's been incredible. NSF funding this is definitely an incredible use of our funds as Americans, and Cornell Tech for hosting, and all of your staff that's helped us today, and for leading this historic moment, the first Open Healthware Conference. And all of you beautiful minds who dare to dream of a free and open world for knowledge seeking and sharing. Thank you, you brave reverse engineers for the public good. My name is Dr. Aisen Chacin, and I run the Medical Prototyping Lab at the University of Texas Medical Branch. And I'm also assistant professor of research in the Department of Pathology in John Seeley School of Medicine. And I'm so excited that we are here in Roosevelt Island. I've learned so much about New York, about American history. I'm actually terrible at history, not my forte, but I found this lab, and it apparently is the first institution in the nation for pathological and bacteriological research. Is just down there. You can take a walk at any time. And that stuck with me because pathology is my home in medicine. And so I read a little bit more about Roosevelt, and I found that he actually had kind of a sickly life and had a lot of health issues in his family as well. And his dad told him, Theodore, you have the mind, but you don't have the body. And without the help of the body, the mind cannot go as far as it should. I'm giving you the tools, but it's up to you to make your own body. And so he responded, I will make my body. And so this reminds me of a quote that I actually always use in my presentations because it kind of distills my domain, which is the human-computer integration world, which says, with every tool, man is perfecting his own organs, whether motor or sensory, or is removing the limits of their functioning. And so I highlight perfecting here because I think perfecting is not just a matter of engineering or science, and it's actually philosophy, right? There's bias in perfection. There's considerations beyond faster, braver, stronger. And my work oscillates between art and science. And these are two cultures that are really kind of blended in by experimentation. I chose to start with sculpture as my undergrad. So I started with art because it was just a place where I could be free to experiment, not have any protocols or give any answers, just simply learn creatively and try to understand perception. As an artist, I was really interested to kind of push the threshold of aesthetics. So perception is the limit of our aesthetics. So if I start making new senses or sensory perceptual pathways, then maybe I can make some really new art. And so looking around the internet, like we all do, open source hardware people, in 2011, as I was graduating from my undergrad in Houston, I found that you could remote control people. And so I was really excited about that. And so I made a galvanic vestibular stimulator, which is a mouthful of words, as you can see. Vestibular system is the system that keeps your balance, and it's in your inner ear. You have 3 semicircular canals that are filled with fluid, and they have cilia, this little metalhead rock star hairs that tell your head where it is in relation to gravity. And it turns out that if you use 1 milliamp on your mastoid bones, you put 2 electrodes and you pass them through, you're able to incite these hairs into moving in that direction. So I hacked a remote control car, put this galvanic vestibular stimulator circuit on it with the Austin hacker space. Back in the day when they used to be called hacker spaces, you know, I kind of don't prefer the word maker as an artist engineer, reverse engineer. But here I'll show you how it works. So this is me in 2011. As you can see, he has a car hanging and he has these electrodes, and you'll see my thumb moving, and then you will see that he starts veering into the direction that I am controlling him to. So the way that's the tree is, you know, I cannot bypass physical reality like that. But anyway, so it worked. He has to close his eyes because, you know, like any perceptual information, it's kind of a conglomeration of senses. And so you have your sight and you have the vestibular system. And so when you close your eyes, then you're really relying on the vestibular system to give you information about where you are in relation to gravity. And so when you're closing your eyes, as you see, he kind of reached out. That means that he feels like gravity is shifting from under him. So he's going to start overcompensating. And that's why he starts walking the other direction. So it's kind of an illusion, but it works. We actually use some galvanic vestibular stimulation for aerospace because the vestibular system with no gravity obviously goes berserk. And then I went to Parsons, where I kind of had this idea from Houston, Dirty South rap, the grills, you know these, right? And so I thought, you know, this is like an arbitrary music object, but it has nothing to do with music, but it's wearable technology. And I had just gone to the Exploratorium in San Francisco and learned that you can hear through your teeth, through bone conduction. And so I made this MP3 player grill, and so kind of mixing rap and science and assistive technology. And then I started looking into research, and I learned about that you can see through your tongue. And so this is an electrovisual experience through your tongue is a matrix of electrodes. And it was invented by Dr. Paul Bacurita, but a few artists had come up with it. And I mean, how brilliant is it that you can make art to see with your tongue? And so I actually was looking around and I found this guy, Zach Hoken Smith. And I said, hey, I found your mouth brain. Everybody puts their own name on it. And I was wondering if you could meet with me because I really didn't understand what's going on. You know, I didn't really have a background in electronics at all. And it turns out, he says, oh yeah, I'm in Shenzhen because I started MakerBot. And so it turns out that I was working with the starter of MakerBot, who I don't know if you guys know MakerBot. I'm sure you do. These 3D printers that kind of started this whole revolution thing. I mean, making it marketing, great marketing. But you know, they sold to Ultimaker for 400 million. So you know, for the people who aren't sure if open source is a great place to do business, look again. So this is Paul Bacurita. He's the father of sensory substitution, and he invented the tongue display unit. As you can see here, he invented it for blind people so that it turns an image of a camera into black and turns that black and white matrix into electric pulses. And so it's like a black and white image. Have you ever licked a 9-volt battery? So every pixel is like a 9-volt battery. I'm sure you guys in this crowd, for sure. And then he used it for somebody who had vertigo and had lost their sense of balance, and put an accelerometer in a hat and then displayed the information of, the accelerometer and gyroscope. And she would wear it and her body started learning or rewiring somehow. And then it turned to a point where she could wear it for 10 minutes, and then she would go 3 months without having to wear the aid and not having vertigo. Um, and in Parsons, I also met uh, Joel Murphy and Yuri Gitman, who are both here, incredibly so. And they've been my mentors of physical computing. They taught me how to program microcontrollers, and because I had just had some basic hardware experience. And you can see, I don't know what he's explaining here, but that's Joel and I. Huh? Yeah, something like, who knows? And they invented the pulse sensor together, which, it's kind of the basis of open healthware in a way. I remember when I taught physical computing, how many people were interested in using the pulse sensor. And it was just kind of part of the response of this biometric data becoming part of, the user experience in common electronics. Fitbit was also starting to get popular at that time. And then we actually shared a studio space in the Pfizer building, Joel and I. I rented a bench from him, and then that's when he started developing the open BCI. And so that was my first shot at modeling. I was a brainwave model. My alpha is really great. And interestingly, I'm working with it again. So really my work falls in between bioart, device art, and kind of a reverse way of biomedical engineering. So for those of you who don't know bioart, this is Stellark. He's also done a lot of robotics, and this is his third ear on arm. And he implanted a cartilage ear on, well, not himself, he had a surgeon collaborate with him. And he also had implanted a microphone because he wanted to hear through that ear. So when artists do medicine and bioart, it doesn't necessarily diagnose or treat. It's more thinking about the body's plasticity in general. Um, and he told me it's such a pain to go through security when they pat you down. It's like, what is that, sir? What's going on? And then for device art and bioart, here's a Iborg, Bob Spence. He was a documentary filmmaker who had an accident and lost one of his eyes, and worked with Dr. Ling in Scotland and made this camera for his eye. Obviously, it's not a digital camera because an analog to digital converter is too big. And so it's an analog camera, and it passes the signal through radio. And he filmed the first documentary from the first eye perspective. And so this made me question the phenomena of electric enhancement to the body may make some forms of disability desirable. Sometimes you look at people with glasses, and I'm a fan of glasses. I love glasses. I wish I was blinder so I could wear glasses all the time. So questioning this, how we are co-adapting with our machines, we are, like Sigmund Freud said, building and removing the limits of our functioning. So now I'm at the Medical Prototyping Lab, which is a space for interdisciplinary collaboration, materializing ideas, conducting research across medical sciences and practice at the University of Texas Medical Branch. And this is my lab. I'm so proud of all my students here. Look at them. I can't wait until they graduate to be my doctors. I'm going to have so many good doctors. Thank you for coming and supporting me in this journey, guys. And this is all the work that we're presenting to you today. Thank you, OSHA, again. Couldn't be possible without you. And so what is UTMB? UTMB is the birthplace of Texas medicine. We were founded in 1891, which is 1 year after the first pathology lab, which is like, oh, wow, there wasn't pathology back then? Interesting. Well, you live, you learn. And this is the Old Red Medical Museum nowadays, where we have some human specimen collections and other things. And it's kind of being built. And in 2015, nurses had this great vision and put in the first medical makerspace inside of a hospital in the US. Obviously, these nurses are not from 2015. But these nurses are. So it was Dr. David Marshall, who was the chief nursing officer at the time, and Dr. Tammy Cupid, the director of nursing science innovation. So incredibly so, it was the nurses who brought this kind of space to the hospital because they have something called workarounds. So nurses are very um, well versed in having to MacGyver things at the bedside, and they call these things workarounds. And so there was a group of MIT researchers, Jose Gomez Marquez and Anna Young, who co-founded Maker Health, which was a company that was studying making at the bedside. And they did a few studies in Guatemala and then brought it to the Texas Medical Center, trying to find a home for their research and do the research again here in the US. And Dr. David Marshall was super happy to oblige, which then turned into the first makerspace. So the space was really founded by nurses, and nurses use them. And this is Meredith. She's the original maker nurse. And she's leaving, so we copied her. And I'll be printing her next week so that all of her colleagues can have a piece of her. I have my ex-boss there too. I'm thinking of turning her into like an 8-ball so that I can still ask her questions, you know? I miss her. And so this is the lab when it was first founded. It totally doesn't look this clean and organized now, so I keep using that photo. But this was funded by the Robert Wood Johnson Foundation, and it was seminal for all of us. So, and I have the luck and fortune to run this space now. So we serve all of UTMB, even though it was put together by all nurses, clinicians, pathology, ophthalmology, anesthesiology. We have lots of schools, medicine, health professions, nursing, and graduate biomedical sciences. We also have the Galveston National Lab. We also have the biocontainment unit for that area. We also have the TDCJ, which is Hospital Galveston. We see all the prison inmates from Texas. So we also have jail in there. And we have a translational intensive care unit, molecular genomics, etc. So I collaborate with everyone there. We also have collaborations outside. We're currently working with the Sasakawa International Space Center of Architecture at U of H. And we took this new model of an EVA, which is an extravehicular activity suit from that Axiom Space is designing for NASA, and studying a framework for virtual reality. And so we took this device with the OpenBCI, and I'm not sure what brand of monitors for VR those are. But we took it on a parabolic flight, and our idea is to try to test all this biometric technology in CROG and see how we can incorporate it into EVA suits. And so, yeah. So what do? We do prototyping. Maybe some of you guys have read this paper, and if you haven't, I really recommend it because it explains kind of like what we do as developers of technology and designers. So it's what do prototypes prototype? And so it explains how a prototype can have 3 different factions: the implementation, which is the technical aspect; the role, which is how it fits within, you know, your user life experience or whatever it is; and then the look and feel, which sometimes in industry is called vaporware. And yeah, have you ever been to like a car show and you're like, that's my dream car, when are they making it? Never, because it's just a shell. You know, this kind of thing, where the prototype looks and feels like it is, but it doesn't have any function. And then finally, an fully integrated prototype kind of has all of these together. So this is the map that I've managed to make about prototyping at UTMB specifically, but maybe it's applicable to all institutions that do clinical research. So first you start with discovery, R&D, you do a prototype and you do some preclinical testing. From there are 3 different offices that we can talk to specifically in our university: the OTT, which will decide whether it's going to be open source or they're going to patent it or they're going to put a provisional and then maybe release it. And then of course the famous IRB and FDA. And so within all of that, eventually, after enough clinical trials, as we saw in Alex's presentation earlier, you can finally publish and disseminate and hopefully get something to market. But as you can see, it's a very cumbersome space. So a lot can be done at the prototyping stage for research. So we also do a lot of simulation models, like some of the students talked about. We do a lot of 3D printing of CT scans for surgery planning. We also have done simulation surgeries. This is a cholecystectomy model, and it's a liver gallbladder model. And so to learn, you have to cut the omentum, and so that's that kind of sheet that you see there. And then you can extract the gallbladder, and then you can clip it, and so on. So they need to practice this, right? We want doctors to practice on living things. So simulation is really good. These models usually cost around $200, and so it's really prohibitive for medical students to buy enough to get the practice they need. And so we remade it, made it 80% cheaper, and made some of the parts reusable, published a protocol and how to maintain it. We also do ultrasound simulation models. This is a ultrasound guided PIV simulation model I did with a nurse. As you can see, we were trying to make a simulation so that nurses can learn how to insert IVs with ultrasound, so you can learn how to see ultrasound. Like, there's a baby in there. No, I'm kidding, there isn't, but Yeah, and so I've been trying to learn how to make visuals for sound to see. And so also taking the opportunity to make them beautiful as well. And so you can see a heart and a circle and some squares and a high. And then going further into ultrasound simulation models, I was invited by the Ionian University in Greece, to do a collaboration on assistive reproductive technology. And so we made a simulation assistive reproductive technology model for ovum pickup. So men can easily donate, their oocytes. Females, we have to go through a whole process where they give us a lot of hormones, and then our ovaries get inflated to the sizes of melons, and then they insert an ultrasound in your vaginal canal with a huge needle, and then they start draining every follicle for an egg. I know. And yeah, I know, medicine sometimes just, makes you a little bit desensitized to things. So I apologize if I'm nonchalant about painful things or something like that. I got desensitized like 5 years ago. So, and so, they drain everything, and then they have the embryologist on site that starts looking through the fluid and making sure they find the ovum. And so here's the process of making this. We ended up using sodium alginate and calcium. And calcium chloride, and to make spherification is a process that you use in molecular gastronomy. Have you guys seen like the vegan caviar? Same. So I made a protocol so that it doesn't solidify inside and it maintains liquid, and so it's ultrasoundable, and you can aspirate it as well. So here you see kind of like the science model, the art model. You see that? Ta-da! Ta-da! Right? So this is much more exploratory research, and I think art has really helped me to be able to translate a lot of the medical needs to technology and for simulation and device making. And this is the artwork. So a lot of times I'll just, somebody asked me once, so how is it that you separate your art and your science? And I'm like, I don't. I try to merge them as much as I can so I can remain passionate about what I do. And so I think of things deeply, not just scientifically. I think of them artistically and philosophically. And so this is, a follicle simulation model that's in a bottle with my DNA. We also make a lot of suture pads, as you saw yesterday, all the demos of the students. This is a critical skill that all doctors need to learn. And from my experience, what they do as medical students is memorize and memorize and memorize. They have these like controllers. Can you guys show your controllers, please? So they have this data. I don't know what it is. It's like an application. It's called Enki. Enki? Yeah, they're flashcards. And so they're constantly trying to memorize all this information. And so when I've seen some of the residents use tools, I'm like, oh, you're a surgeon? Have you taken a sculpture class in your life? So anyway, simulation is really good. I think people need hand-eye coordination in medicine quite a bit, and sometimes we don't elevate this as much. So we made this suture pad with silicone, and we made a protocol that was also published, and to make the layers of the muscles, the layers of the fascia, the layers of the fat, and the dermis. And we also try to make the texture of the skin. And then we moved into biologicals. We use these bacteria to make bacterial cellulose. And so here you can see phase one. You grow the bacteria. We're using sugar, and we're also using tryptone, which is short protein, which bacteria can digest, and so they can make these cellulose. And then you suture it, and in 1 week, essentially it heals. So here you see it. So, the tensile strength and the cellulose make it so that it's, much more realistic. And so then you put it back in the brine and it heals, so you can remove the sutures. The fact that it's alive is also great because it teaches students about hygiene. You can get it infected. So we're working on making that into a kit. We've also done a leg fasciotomy model, and I'm just going to go through all this stuff quickly because we do a lot of stuff. We also made tactile directives for low vision and blind patients because they can't read how many drops they have to take for their medication, but they could feel them. And so we have these. And then during the pandemic, which is kind of the basis of this whole meeting, I guess, is what really spurred us to come together. We made URUS, the emergency use resuscitation system. Luckily, we were in a hospital, so we already knew about all the regulatory issues before we started doing a lot of, big changes. But with that, we tried to design this. We heard the call, we need more ventilators like all of you guys did. And we tried to do the Apollo 13 thing, I'm like, what do we got? Open the closets, supply closets. And then I thought, okay, I'll use a blood pressure cuff inflated with the vacuum and air from each patient room has ports for vacuum and air, and then inflated and deflated at the rate. And I found a quote that fits from Theodore Roosevelt: do what you can with what you've got where you are. So this is it. And those are the schematics, which is all in GitHub. And so we made it so that it works at the top. So 800 milliliters of tidal volume at 30 breaths per minute is our best, and that's pretty close to benchmark. I think benchmark is 45 breaths per minute at 800 milliliter of tidal volume, but we got that at 450. And thankfully we had vacuum because otherwise you couldn't get it fast enough deflating naturally. So this is when we actually did the animal studies. We ventilated 3 sheep and did it successfully. The first 2 were for 30 minutes and the last one was for 2 hours, and it blew my mind. I can't believe that we built something that sustains life. And as an artist, I distilled it as well. And so this is called First Breath and this is called Last Breath. 2 artworks that kind of, honor the sheep. And then I did a meditation about animal sacrifice, the cycle of life, the persistence of survival, and the anatomical, mechanical, and chemical functions of breathing in collaboration with all these beautiful people. And really, as an artist doing animal testing, it was really hard for me. And so and talking to my students that have to snap the necks of mice a lot and don't know how to deal with those emotions, he said, sometimes I say a prayer when no one's around. So that made me a little bit concerned about how we are dealing with this kind of thing. And so I thought that a meditation would be a non denominational way to do it. And lastly, I want to remind you guys the Hippocratic Oath. I swear by Apollo, physician, and Asclepius, and Hygeia, and Panacea, and all the gods and goddesses, making them my witness, that I will fulfill, according to my ability and judgment, this oath and this covenant. And I want you guys to look at this. To hold him who has taught me, if he is in need of money, to give him a share of mine. Students, the oath makes you give me money when I need it. I just want to point that out. And lastly, it also says to teach them this art if they desire to learn it without fee and covenant, to give a share of precepts and oral instruction and all the other learning, which I thought is beautiful for what we do as open source developers. So, lastly, I think collaboration is the basis of knowledge. And something that I've learned around the years that I've been around is that a good collaboration is founded on mutual admiration, which is a glue for trust. If you admire somebody, you're probably going to trust their opinion. And if they admire you, they'll trust yours. And so we can collaborate and fully enjoy each other's contributions. So if you have any ideas or questions, please email me. I'm super open to collaboration. I do what I can to maintain all my projects. I figured out that if I have students, I can put legs on my projects and they talk to you, so they get done. It's been an incredible system, and so I'm happy to work with outside institutions and individuals that are interested. So thank you very much.